Hello everyone, I bid to the audience. I am Dae Song, presenting Group 14 for the introductory part of the video. First, let me introduce you to the members, which are Agatha, Junchen, Kelly, Yushen, and I. Without wasting any time, let me start my presentation. Lumbosacral orthosis, also known as LSO, is an orthosis that functions to support lumbar and sacral region of the spine. In this condition, we assume the LSO is made of polypropylene, and the aim of this assignment is to understand the mechanism of LSO through the study of mechanics of materials. Next, let me give some explanations about axial and torsional load. Axial loading is the forces that are experienced along the axis by a beam, whereas torsional loading is the forces that generate torque or causes the beam to turn. Nevertheless, these two types of loads generate stress and strain towards the beam and results in deformation. Furthermore, there are different types of stresses that we will be discussing further in this video, which are axial stress, bearing stress, and shear stress. Lastly, deformations. Deformations cause the changes in shape of material. These deformations happen due to different types of stresses exerted on the beam, and we will be discussing about deformation further in coming examples too. Thank you.
Hi, I'm Agatha. Now I'll explain about the first learning outcome of our real-life case, which is solve problems involving a body under the action of axial and torsional load. First and foremost, let us have a look for the free body diagram of the lumbosacral orthosis where it's bearing on the scoliosis patient. FA and FB indicate the reaction forces of beam, N1 and N2 indicate the normal forces of beam, F1 indicates the resultant force of beam, and MA indicate the moment produced around the axis of FA and N2. Several assumptions have been made, such as reaction forces of beam FA and FB equal to 500 Newton, angle between beam and bone equal to 10 degree, angle between FB and F1 equal to 15 degree, and length of beam equal to 0.4 meter. For ellipse, the A out equal to 32 cm, B out equal to 11 cm, thickness of beam equal to 0.1 cm, maximum shear stress of beam equal to 300 megapascal, and the modulus of elasticity equal to 4.5 gigapascal. For axial load, firstly, we can redraw the free body diagram and identify all the forces acting on x-axis and y-axis of the beam and the bone. By using the equilibrium equation, total forces acting on x-axis equal to 0, we can obtain the first equation. After that, we can do for the total forces acting on y-axis equal to 0 to obtain the second equation. The third equation is obtained by assuming the moment produced around the axis of FA and N2 equal to 0, and anti-clockwise direction is considered positive. After obtaining these three equations, we can solve them simultaneously to find out the unknown values of N1, N2, and F1. For torsional load, since we have considered the beam is a hollow ellipse, hence by using this formula, we can get the polar moment of inertia equal to 3.2 times 10 to the power of negative 3 meter to the power of 4. The torque can be calculated by taking the maximum shear stress of beam multiplied with the polar moment of inertia and then divide by the radius of the beam, so we got T equal to 7.5972 Newton meter. That's all from me.
Hi, I'm Junchen. Now I'm going to discuss about level 2. For level 2, it's required to solve the stresses in the beam. There are a few stresses can be solved in this real-life case, which are axial stress, shearing stress, and bearing stress. To calculate the stress of each type, the formula of stress where P over A and P refers to the force, while A refers to the area, will be used. While calculating the axial stress, the force had to act perpendicularly to the area. From the free body diagram, you can see that P equals to F1 sine 15, while the area is calculated using the formula where area equals to pi AB minus AB to determine the area of a hollow LSO, and then the LSO is in the shape of ellipse. Through calculation, the axial stress is 191.77 kPa. The stress value was set too high, as the spinal can withstand about hundreds of kilograms of pressure and can only support compressive loads of thousands Newton while walking and standing. Too much stress exerted will cause fracture at the bone. Next, we determine the shearing stress of the belt. When calculating for it, P will equal to F1 cos 15, as the force should act parallelly with the area. Due to the shape of the belt is rectangular, the area of the belt can be determined through the formula, where area equals to TD, and T refers to the thickness, and D refers to the diameter. The calculated shear stress is 3.849 MPa. The shear stress value can be higher, as the maximum stress can be exerted. It depends on the materials of the belt. Lastly, we calculate for the bending stress of the contacted edge. We can find the area using the formula where A equals to TL, T refers to the thickness, and L refers to the length, while P will equal to F1 sin 15, as the force should be in the same direction with the area. Through calculations, the bending stress is 4.811 MPa. The value of bending stress should be higher because the bone will get straightened due to this stress. Therefore, to reduce the angle of scoliosis, the value of bending stress must be higher.
Thank you, Jin-Chan. I'm Kelly, and I'll continue with the LO3. In LO3, we will evaluate the stress by calculating the strain and the deformation of biomedical device due to the compound load. So, strain is defined as the deformation or displacement of material that results from an applied stress, while the deformation refers to the modification of the shape or size of an object due to the applied stress, such as axial stress, bearing stress, strain stress, as listed in the previous slide. So how are we going to calculate those strain? For axial strain is calculated using the axial stress over modulus of elasticity. For our group, we have decided the modulus of elasticity is 4.5 multiplied to the 10 to the power of 9 gigapixel, as we have obtained the average value of modulus of elasticity between 0.008 gigapixel to 8.25 gigapixel. So the axial strain is calculated as 4.26 multiplied with the 10 to the power of 95, while the deformation of beam caused by the axial strain is calculated using the axial strain multiplied with the length of the beam, which is 0.4 meter, and is calculated as 1.70 multiplied with 10 to the power of 95 meter. Next, for shearing strain, is calculated same as the axial strain using the stress over modulus of elasticity, and is obtained as 8.55 multiplied to the 10 to the power of 94, while the deformation of beam caused by the shearing strain is calculated using the shearing strain multiplied with the diameter of the beam, which is 0.05 meter, and is calculated as 4.28 multiplied with 10 to the power of 95 meter. Moving on to the bearing strain, the bearing strain, we are going to use the bearing stress over modulus of elasticity, and is obtained as 1.224 multiplied with 10 to the power of -3. In LO2, we have calculated the bearing stress at the contacted edges. So in bearing strains, the deformation can be classified as two types, which is deformation of beam caused by the bearing strain and the deformation of belt caused by the bearing strain. So for the deformation of beam, we are going to calculate it using the bearing stress multiplied with the length of the beam, which is 0.4 meter, and is calculated as 4.896 multiplied with the 10 to the power of 94 meter, while the deformation of belt is calculated using the bearing strain multiplied with the diameter of the belt, which is 0.25 meter, and is calculated as 3.06 multiplied with the 10 to the power of 94 meter. And it's all about LO3. Thank you.
This is Yushan, and now let's move to the conclusion part. In this study, we have done 3 learning outcomes for a lumbosacral orthosis, and a hypothetical method was used to assume the data of an LSO in calculations. A free body diagram of bones and beam was constructed, and a study was based on assumption data. This series handles issues involving a body under axial and torsional pressure, stress in beam, evaluating stress and deformation of biomedical devices, owing to a compound load, and presenting ideas on a variety of materials concerned in the biomedical engineering sector. Meanwhile, we have studied how the pressure is exerted by lumbosacral orthosis with our design orientation and how it produced through the study of mechanics. And finally, thank you for watching.